conflict with each other. The knowledge from code base, you report this is a misuse, but according to the knowledge from text, this is not a bug. So how do you deal with such problem?
This is an interesting question. There indeed may have inconsistencies in code and elements. But in our definition, there are just two basic types, Boolean and set, and we don't know which specification from the specific source is correct. So we just make a disjunction and a unit set to let them work together. So don't waste the analysis results. Maybe this can.
How these methods are actually implemented. So did you try to look at the code of the API implementation, right?
Yes, I think the code API implementation is an important source. But if we need to analyze the API implementation itself, then we need to get not only get the code base we need to check, but also collect the code of the library.
Yeah.
So it's yeah. But if we can analyze the API implementation, then we can get some basic metadata such as the literal value type or arguments, the data type of the arguments.
Okay, but you didn't try to explore that direction.
Yeah, I tried some, but I think the implementation, because we indeed the analyze way, even if we get the data type, then we don't know whether actually need to check the data value or check the data type of arguments. So we think we can cross-check, make a ranking or voting scheme to cross-check each other is possible.
Okay, thank you.
Thank you.
We have time for one more question, if there's any room.
Yeah. Thanks. Michael Schlichtig from Paderborn University. Just an idea. So you derive the specifications of how to use an API using natural language processing, right? Could you maybe reverse the natural language processing to put in, use specifications as input to create documentation in natural language? Would this be something that's feasible?
You mean for other language, the misuse of other language?
Let's say you have specified how to use an API in a specification language. Could you use natural language processing in a reverse way to create documentation?
I'm afraid I didn't catch your...
yeah, okay. Was
maybe
more like...
have a talk after this session.
Yeah, awesome.
Sorry,
Thanks.
all technical issues.
Sorry.
All right, well, let us thank the speaker again. Thank you. All right, so hopefully we'll get the second third talk going. All right, it looks like it's working. Are we able to share a screen?
Hello.
Yes, we can hear you.
Hello.
Hi there, we can hear you, but we're trying to figure out how to share your screen. Just one moment, please.
Hello, yeah, we can hear you. We're just figuring out some logistics of sharing your screen. Do we get to see his picture too, or video? I'm gonna, take what I can at this point. All right, so our next speaker is Chen Yang from Army Engineering University of PLA, and he'll talk to us about compatibility issue detection. So please go ahead.
Good morning, everyone. My name is Yang from Army Engineering University of PLA. I'm so glad to present our work, Compatibility issue detection for ambiguities based on cognitive semantic analysis, which is a joint work with Tianjin University and Nankai University. Along with the high-frequency updates of the Android operating system, any evolution of the APIs may cause compatibility issues due to the fragmentation problem of Android, which may inconvenience end user and significantly degrade user experience. Popular APIs also suffers from the compatibility issues. For example, APP and OTP had a UI inconsistency issue. It incorrectly loaded with default icons and on Android 6, which is not the real icons. While on Android 7, it correctly loads the icons. Besides this type of issue, APPs also suffers crashes, functional failures, performance loss, and other compatibility issues. However, there are still many deficiencies in existing solutions caused by neglecting the context semantics of checking patterns, leading to a high false positive and a high false negative rate. And some developers also complain that automated analysis tools are rarely correct. So in our study, let's first see a real example of the popular APP named GPS test. In GPS test, the class utils is used to check the runtime APP versions with the method write_JNS to field in worker and in compatible API. From this example, the analyzed changes can summarize as first, the extraction of different check patterns across different classes. It can be reflected by extracting the constraints of as granted permission and analyzing which pattern it belongs to across all classes and static methods. The second challenge is semantic analysis of constraints in each API as considering the API lifetime. In fact, it also challenging to accurately model the lifetime of APIs due to different type implementations and different Android versions. However, existing technicals only check whether the runtime API version is checked directly in the if clause, which neglecting other semantic condition types or other patterns cause many false alarms. And we highlight the main differences between our work, PS joint, and existing study in table 1. The column semantic analysis refers to whether the tool analyzes different semantic representations of constraints in different API using check patterns. The column passive sensitive analysis refers to whether all paths that are relevant to the incompatible API range are taken into consideration. From those two columns, we can see that none of existing methods analyze different implementations of using patterns for their detection or repair tasks. which could lead to many false alarms in practice. With our tool, Joy, leverage a semantic analysis method that is sensitive to various API using check patterns when detecting compatibility issues. Based on the previous investigation, we aim to propose our method, Joy, which is a passive approach with semantic analysis. It can automatically detect incompatible API usage in Android PCs. It takes IDP as input and outputs all compatibility issues and incompatible invoking methods. And the Joy contains 4 key pieces. First, path localization. Second, passive semantic analysis. Third, lifetime modeling based on API semantic analysis. Fourth, API compatibility issue detection. Let me explain these pieces in detail. The most common practice of check pattern is check the value SDK int in a directory in the if clause. Apart from checking the runtime SDK version in if statement, developers can also use ternary expressions as a constraint to invoke the specific APIs. And the third check pattern is static field check. It obtains the runtime SDK version check by defining a static variable or static method, and the runtime SDK version is indirectly checked in this variable or method. The more details can be referred in our paper of this check pattern. And the fourth check pattern is check pattern. This pattern is to invoke potential incompatible APIs in a check statement, which is commonly used when developers use unfamiliar APIs, for example, in APIs in third-party libraries. To investigate the frequency of those 4 patterns in real world, we investigate more than 600 real-world APIs, and we found that nearly 40 developers use all those 4 types of check patterns in their app. So we need to analyze the semantics of all those 4 check patterns. Joy perform a CFG-based analysis to match those check patterns with the API or the record method in the past. Besides summarizing and analyzing those 4 check patterns, we also summarizing the API lifetime augmentation. This slide shows that why we augment the API lifetime. First, we found that the APIs with the same semantics have different declarations in SDK version 1 to 31. Second, the Android framework introduced constant in SDK after SDK version 29. Third, such inconsistencies may lead to incorrect API lifetime. And consequently, the ways how we treat those inconsistencies are like, first, we summarize the types of such API updates inconsistencies. Second, we unify the inconsistent API to one API. Last, we build a refined lifetime database. Let me explain those 4 with the summarization of 4 augmentation types. First, a notation that can return value type. Third, extends method. Fourth, generic type. And more details can be referred in our paper. And last, based on the directed SDK-related patterns along each path and the augmented lifetime of APIs, we aim to identify whether the API has potential incompatible issues by comparing the runtime constraints of SDK versions to invoke the APIs and the lifetime of APIs. So here is the example. If our runtime does not include in our life, which means there might be a incompatibility issue. In evolution and effectiveness, we compare PSJOY with our fast state-of-art detection tools on 3 datasets. And we also reported 3 real issues to developers for their feedback. We first built a ground truth dataset containing 12 APIs that cover different types of compatibility API usages. And we found that our method can effectively different types of incompatible API usage, which covers 1% precision and recalls, while other 2 state-of-art toys only achieve nearly 60% recalls and precision. And we also obtained the version before and after the commit of revising compatibility issues to construct our baseline dataset, which is shown in table 4. And we also found that our tool PSJOY can effectively detect the compatibility issues with high precision, which is nearly 94%. In Arc 3, to demonstrate our the tool advantage compare with other 5 existing compatibility detection tools, we compare them on 645 APPs. And the result shows that PSJOY outperform existing tools in elevating false positives and false negatives. And in our paper, we also highlight the combination result in our paper. More details can be found in our paper. At last, in our reported 30 issues, we received 18 feedback, and of them 6 issues are fixed, and 9 issues are confirmed. Remaining 3 issues are responded, and the other 12 issues we reported also confirmed by ourselves. And we received many positive responses from developers. For example, for APP Anki Zhao, the developer finally recognize our detection tool, as it can help them find real things in their APP. And if you want to use our tool, you can find it here. It's available on GitHub. Thanks for listening. I hope our work can better get practice in the future. That's all. Thank you. Yeah. Pardon? Can you speak more slowly? Okay. What pull request? Okay, I has not summarized the pull request in GitHub. You can see after the representation. Yes.
named third party. The list of the third party library are copied into this folder. For example, the libpng, which is a famous third-party library, and their code are directly copied into this folder. And so does many other libraries. To use this third-party library, it will bring many convenience, especially if we want to develop some similar utility, using the third-party library will be save a lot of time. But it also will bring more security issues, especially when you those has high exposure to the hackers. And for example, the CVE is the name for common vulnerability and exposures, and it has published over 30,000 CVE on the NVD websites, and all these CVEs are related to the C and C++ library. And when you using this third-party library, and if you don't know the security issues behind them, you will maybe exposed to very vulnerable situations. So it's important for us to check down what third-party library are we using in our projects. And that is our main focus today. And there is a tool named SCA, which means software compositional analysis. And these methods are often taken as the main method to check out what the third-party library are you using in your projects. But for the C and C++, the situation are special because there are no official package manager for the C language. So to use the so in the C open source system, and people are using the third-party library in 3 ways. The first is using some package manager. These package managers are not official. They contain only a small part of the libraries for the user to be used. And the second one is the build system, which are widely used for many of us, especially for using the binary, like the one on the Debian or Ubuntu. And the third one is the most common way, code clone. Code clone means that people just copy or do some slight modification for the code and then integrate it into their development projects. And if the people are using this way to copy the third-party library, can we just use the code clone detection methods for tracking down the third-party library? Because code clone detection has been developed for many years. There are many mature tools for detect the clone mapping and with very high accuracy and high efficiency. But the situation is that if we directly using the code clone, it's not sufficient because code clone detection are not equal to the third-party library detections. Here is a concrete example. When we do the TPL detection, we need to previously collect a list of libraries. And for example, library A is, if I collect a library A, many of those pre-collected library are containing the code of other library. For example, the T1. T1 in the library A is another library that being copied to the library A. So when we scan the target projects, which happen to contain the T1 as the third-party library, the code in the target project will be mapped to the code of the T1 in the library A. In these situations, even though the target project does not contain the library A, it will also falsely report library A is its dependencies. And so to avoid these situations, and the state-of-the-art scientists have been proposed a method to increase the accuracy. For example, still the same library A, and because the code of the T1, it can be recognized as a copy code in advance when we build a database. So the scientists will remove all this code as the feature of library A. So in this situation, the target project, when we scanning the target project, we will not report the T1 again. In this way, the false positive will be largely reduced. But there is some limitation on this project too, in the Centris too. Centris, which is the state-of-the-art tool we compare to. And Centris will also using a threshold for conforming the TPL detection. The threshold means that when the matching rate between the target project and the library are larger than this threshold, will they report the library A? For example, if the library A in the target project has been copied over, let's say, 50%, and the function of the mapping rate for the functions are over the 10%, and they will report the library A. But this will bring two issues. First is the false negatives. False negative means that there are some library will be missing for the during the scanning, especially for those partially used. In the C ecosystem, when we're using a library, we does not simply copy all the code. We may copy only one function or a small part of the source code. So it won't be necessarily 10%. If only 1% copy, and they will miss this case. Also, the false positive is the same. Is another aspect that will cause issues, because even though we use the matching rate for mapping all the self-return functions by library A, but there are some very trivial and common functions that should not be used for mapping the library A. For example, the left side, some sample function from the OpenSSL. The function is simply contain only return 0, which is a very simple function that this function cannot represent the OpenSSL. OpenSSL is a library that deals with the network and protocol problem. So we need to come out a new solution for this problem. And our assumption is that if we only keep the core functions from every library, by core function we mean that the unique and significant functions for each library, and only one function are matched, we can directly report the library A. In this way, we do not need any thresholds. Only those partially used case, even if those partially used case and only 1% of them are copied, we can still detect them. And so, what are the core functions? Here we will give a definition for all function types. We divide the function into 4 types based on some aspects. The first type is clone function. Clone functions means that those codes are not written by yourself. It's copied from otherwhere. This is different from the other 3 types. And so for the third type, supporting functions, its main difference is that they do not contain any logic. As a previous example, so some functions like return 0, all those setter getter we may usually write, these are not containing algorithm or logic. They are very simple. They do not unique or significant to any library. And so the remaining 2 types is the core function and common function. Common function and core functions are certainly contain, or they will contain certain logic, like those like algorithm, math library. But the difference between the common function and core function is that common functions are widely used in almost all the library. They are not special to the specific library. They are just implemented to support the core algorithm of the library. So here is our operation experiment for filter out all those non-core functions. If the functions are filtered one by one, our accuracy are hugely improved. That means that all those non-significant functions are not necessary for the TPL detections. And also our efficiency will be improved because we don't need to calculate the thresholds for each library one by one. We just build a hash index to match only one function to report the target library. And here is our overview of our method to constructing the database. The first and second phases are mostly focused on how can we handle the data problem, because we need to clone the repository, we need to deal with the version problem, we need to pass the function out of every file. So these two types, we also done some optimizations. And the third phase is our main algorithms, which how can we filter out those non-core functions. And here is our main phase. For starter, the clone functions are very clear because their commit time must be later than the commit time of those libraries who created them. So if we are using the same function from the other library, the commit time will be, the number of the commit time will be larger. So for those clone functions, we can easily filter them out. And from the other two types, the supporting function, as we mentioned before, they have very low code complexity. The code complexity, here we will use the maintainability index to measure them. So those with high maintainability index will mean that they have low complexity. We will filter this supporting function by this aspect. And for the common functions, they may share the similar code complexity with the core functions. So the difference is that they will appear more frequently in the overall open source systems. And so the TF-IDF will be suitable for this situation, but we will simply use the document frequency. Document frequency here means that the number of libraries which contain the same functions, and those common functions will appear higher in the open source systems, so their document frequency number will be higher than the core functions. In this way, we can filter this out. And of course, for the supporting function and common function, we may not know how much proportion will it have, because either it's 50% or 30%, we cannot know for each library. So we will do a experiment for those distribution for how much proportion will the supporting function and common functions be. And through this distribution accuracy heat map, we can compile a proposed number for this thresholds. And after we select the true thresholds for filtering the common function and supporting functions, our accuracy can be hugely improved. And also it can outperform the state of art in both precision and recalls. And also, although we using the core functions will hugely improve our precision and recall, but there are also some false positive cases. But these cases are not coming from the partially used cases or the common and trivial functions. And they simply because our data scope is not complete. When we are lacking one library, for example, the library N, if we don't collect it in our database, we will take the part of the code of the TPL in library A as their core functions. In this way, we will still forcibly report the library A as a dependency to the target project. And the version problem is also the similar. So to improve our detection tool, our future work will focusing on how to complete the data scope. Currently, for our experiment, we also collect 24,000 GitHub repos for which are over 100 stars for our constructing our database. And this is not complete, and we haven't figured out what's the actual size of the C libraries. And also, because the C also has some poor version management problem, and we also aim to fix these two issues in the future work. And thank you. This is our point.
Any questions?
Thank you for the nice talk. I just want to understand the motivation. I don't clearly understand the motivation. Like, why do you need to search the third-party library from, who is the user of this tool, basically?
Basically, almost all the application project will be using this tool, because when we're using a third-party library, the third party may bring some security issues. If you know what third-party library are you using, you will know if there are security issues attached to them.
But what I don't understand is that I'm developing some project, and then I'm trying to use some library, and then I don't know the library. Is that what you're saying? Like,
yeah.
Oh, really? But that's for me is like quite.
Yeah,
okay.
thank you.
Do you know the library
Okay.
that you're going to use, or you don't know it? I guess that's.
I mean,
yeah.
if you want to use some third-party library, which is open source, you have to include it, and then you have to also include their library, their licenses, because of the license issue. And then,
okay, I understand your questions. Actually, our tool has been commercialized. For those large companies that we use our tool to scanning all the project under development, because some developers, they will not clearly report their third-party library to their vendors. So they may need to scan all the third-party library to find out the security issues.
okay, yeah, I get the point. Yep.
Also,
Thanks.
okay.
Can we take it offline? We're running off really over time. So there's another question for you if you want to take it offline.
Okay. Yeah.
Maybe find the question after.
Sure.
Okay.
Okay,
All
thank
right,
you.
Thank you very much.
So this is a joint work with my colleagues at ASAP, Sheffer, Branavan, and Ippolito. And as I said, this work was developed under the context of ASAP, a company that sells AI solutions to enterprise business or companies. And to motivate the problem we aim to solve, I will start in the next few slides simulating a conversation between an end user of one of these enterprise business companies, imaginary one, and a contact center agent. And as you can see, the end user wants to know his or her account balance. Now in the left side of the screen, you can see the agent's view, that is the dual or corresponds to the dual of the end user view. The agent is using an AI tool to auto-suggest responses to simplify his or her work. In ASAP, we call this tool auto-compose. And in standard workflows, the things that this tool can suggest is very generic, like, let me check in a minute that information from you. That limitation is mainly due to the fact that the information that we need to check is stored in the enterprise company's databases or systems. So what happens is that the agent must go and look for the data in the CRM of the company, and then come back with the data and write it down in the chat window. Clearly, this process is inefficient, and ideally, we would like the response to be suggested by the ML tool directly, streamlining the interaction. So concluding the introduction, one main or key assumption of our work is that not only high-quality training data, but also real-time data and ongoing updates is crucial for AI-powered solutions. The question then is, where can we find this high-quality data to leverage from? And it turns out that there exists a whole huge ecosystem around web APIs that seems to perfectly match with our goals. And it includes not only public or public APIs with relevant business information, but also enterprise companies that share private data through web APIs to authorize third parties like ASAP that offer services to them. So to be able to efficiently process all this potential data, our paper presents an approach to scale web API integrations. And as we delve into our solution, it is important to understand that there are two sides of web API stakeholders in a software platform. On one side, we have the data consumers. On the other hand, we also have the teams responsible for integrating the data into the system. So let's start with the consumers. In big software platforms like ours, there can be a lot of different services that needs to consume data from web APIs. In the context of ASAP, our company, we also have, besides AutoCompose, also AutoSummary. And there are also many internal sub-modules in each of those services that needs to consume different data. On the other hand, each modules need to consume data from every different customer. So assuming, for instance, we have these services providing value for different banks, what we end up having is a nen.m kind of problem, where n represents the number of internal modules consuming data, and m represents the existing universe of web APIs. To tackle this explosion of dependencies, we propose using an ontology-based data access approach in which a single unified and agnostic ontology is queried by every module, and then the ontology translates these queries into the respective APIs depending on the customer the agent is currently chatting for. So in this manner, we simplify the data consumption by effectively decoupling the internal systems from the diverse external data sources, thereby reducing the complexity to an n plus m problem. Now let's discuss the integrator side of our solution. The main challenge for the integrator is efficiently integrating all existing heterogeneous data sources into the ontology. To enhance this process, we first introduce a domain-specific language we call the integrations block language. The IBL enables domain experts, but not necessarily professional software developers, to easily specify integrations. And briefly, it is a simple functional and graphical programming language based on a minimal set of nodes for performing the most classical integration operations such as data retrieval and transformations. To further support the language in the paper, we have formalized both its syntax using graph grammars and also its semantics using CAM process network simulations that are a model similar to Petri nets for those more familiar with that theory. Unfortunately, for the vast number of web APIs requiring integration in a platform supporting many enterprise customers, even with the domain-specific language, a manual approach to implement this integration remains slow, expensive, and error-prone. And to address this issue, we also propose a process for automatically synthesizing integrations. To do so, giving an ontology, a set of API sources, and a mapping between fields from both schemas, we characterize the integration problem as a classical automated planning problem. And we already know where the ontology comes from, where the data API sources came from, and what about the mappings. So we use NLP techniques to automatically suggest relations between fields in the ontology and fields in the API to be integrated. In the slides, you can see an example of the front end we are currently prototyping to support the mapping validation. And after somebody in charge of integration selects a field, for instance here, the field name first from the account info entity of the ontology, two mapping suggestions appear on the right of the panel, on the right-hand panel. And these are fields existing as part of the response of an endpoint in the API. And for each, we also show a score that represents the confidence the NLP model has about this suggestion. So finally, once the mappings are provided, when a data consumer executes a query, we first translate the query into a goal for the planning problem. It consists essentially of a set of fields from the ontology to be returned. We then compute the planning policy, and it will contain the endpoints that need to be hit in the API, as well as the transformations needed to compute the ontology fields based on them. We finally translate that policy into an integration block language method with a synthesizer. And yeah, that's all. So results, by employing the ontology-based data access combined with the domain-specific language, we have managed to improve our timings for web API integrations by 50% in time. One significant factor contributing to this result is the substantial reduction in cross-team overhead achieved by providing the right tooling to our API domain experts. And moreover, a preliminary implementation of our synthesis approach have shown already a promising additional 25 improvement in time. That's all. Thanks.
Great, questions?
Very nice work. Thanks for the presentation. What about schema evolution? Maybe that's the short question.
That's a problem. So we haven't approached the problem yet, but we are thinking on trying to also leverage our ML models to try to automatically help with the evolution. But yeah, for sure, that's problematic.
There's another question in the back. Can the next speaker come up probably?
Thank you for the great presentation. Quick question. Assuming that we are a company, we have, I don't know, 1,000 or 5,000 of API exposed because we are an international organization, we are using open API, open banking, and this kind of stuff. How complex it is to use your solution to integrate it in our company and make it work at scale? Is it like 3 months work, 6 months, or is it a private code, private technology, or can we benefit from your contribution to put it in production from our side?
It's a private technology. Let's say that the paper somehow shows how to generalize it or how to create your own technology based on the results. I would say that once the technology is there, it's easy to integrate with it. The only important thing you may have to do is create your own ontology with a kind of uniform language for your internal system. But once you have that, the integration with the technology should be 3 months, not 1 year. From my point of view, I haven't tried.
Okay, I think that's all right. Well, thank you very much for the nice.
Thanks.
Hello everyone, I'm Pasala Thanakiankai, D2 student from Nara Institute of Science and Technologies. Today, I'm going to present our paper, Giving Back Contribution Concurrent to Library Dependency Changes in a Software Ecosystem. And this work was published in TSE in the April 2023. So, the adoption of third-party libraries for software development has led to the creation of large interdependency networks such as NPM for JavaScript, Maven for Java, and PyPy for Python. However, sustainability issues of a single library can have widespread network effects. And Maintenance of this library are often overworked, relying on the contribution of volunteers to sustain the libraries. For example, these maintainers of a library express their frustration when maintaining the library in a tweet. Therefore, it is important to find the help to support these maintainers to sustain the libraries. And in this work, we look at the one possible contribution that can support the maintainers, which are the contribution from the client package. And we investigate how contributor of client package submit contribution to access the libraries in this work. And this is the example of contributor whose code depends on a library submit a contribution to access the library. In this example, the developers that using this library create an issue to ask the maintainer to accept the pull request. And to understand this contribution, we borrow the ideas of socio-technical congruence of Catado to define the DC congruent matrix or dependency contribution congruent matrix to measure how closely the network of dependency changes match the network of contributor changes. Then to calculate the DC congruent matrix, we create a dependency network, and we also create the network of contributor changes. And because we focus on the client contribution, so in this work we look at the contributor who contribute to both client and also contribute to the library. And the DC congruent is largest when the contributor contribute to both the client and their dependencies. With this metric, we can explore the degree and origins of dependency contribution. And in this work, we look at the 4 different types of dependency change, which are add, remove, upgrade, and downgrade. And we also define 4 types of contribution that based on the contributor role in client and library package, which are committer and committer, committer and submitter, submitter and committer and submitter and submitter. That the committer is a developer who can merge any submit contribution, and a submitter is a developer who can only submit contribution but cannot merge the contribution. And we measure the DC congruent within the NPM ecosystem with the issue, pull request, and commit of 100,000 different library. As you can see, the most dependency contributions originate from the contributor who can only submit to both a client and a library. And we also find that DC congruent could be used as an indicator of libraries at risk of becoming dormant. And dependency contributions are not typical contribution by that contributors. Based on this result, our research may identify fragile points in the dependency network and may ultimately encourage the dependency contribution that support the maintenance of interdependent third-party libraries used in the software development. And our take-home message is in the title, Giving Back to Community. And that's all about the presentation. You can access the paper via this QR code. Thank you for your listening.
Any questions? Right, I had one. So is the base assumption that a contributor should not contribute to both a library and its dependencies? So is that better or worse? I didn't understand like the base assumption.
Yeah, our assumption in this paper is to help the maintainer to sustain the libraries. I think the client that using the library should contribute back to the library, to help them, because the maintainer always overwork without paying. Yes.
Okay, got it. All right, well, thank you very much.
Hello, everyone. My name is Lina, and the work you're going to see now is a joint work with people working in Labri in France. The paper was submitted to the Journal of Systems and Software, and this one talks mainly about breaking changes and its relation to semantic versioning, and also the impact they have on client projects. But before I start talking about the paper itself, I would like to share first the problem we're addressing here. So basically what we have in the world is a set of projects that depend on each other. Here you see that each dot represents a release, and each release is usually versioned. So here you see that we have a project, a client project, version 1 and version 2 of that client depend on version 1 of the library. But at some point, the library evolves and it might introduce breaking changes. What are breaking changes and what is the definition of a breaking change? It's a change that can potentially impact a client project. And notice that I'm using potentially because sometimes this does not really happen in the wild. So the thing is that every time we see that we go from this major number 1 to 2, it is according to semantic versioning, it is informing us that we're introducing breaking changes. So for us as clients, sometimes this might be scary. We tend to associate breaking changes with harm in general. So what we really wanted to know was, okay, we are indeed introducing breaking changes, and there are actually quite some tools that can detect them, especially in Java. But what is the real impact in client code? What is the size of that problem? So to address that problem, we try to find some examples or some studies in the state of the art, and we found few of them. Except for this one, it was a paper published by our colleagues in Delft, by Stefan Rijmakers, Adi van Dersen, and Joost Visser. And this was the paper that approached the best the problem we wanted to understand. So we decided to perform a replication study of this work. And basically what we did is that we selected a subset of the questions they posed. And we tried to improve the protocol based on their own lessons learned, but also on the points that we thought could be improved in general. For instance, the way how we could detect the impact on client code. In this regard, what we did is that we implemented a tool that, using static analysis, can tell you if a breaking change introduced between two versions of a library will impact your code. So that was the major change there. The second thing is that we also used a bigger data set, a more recent data set. It was bigger because it was more recent, of course. So the first question we wanted to address was, how are semantic versioning principles applied in Maven Central in terms of breaking changes? And when I'm talking about semantic versioning principles, here I'm mostly focusing on the use of the major number as an indicator of the introduction of breaking changes. So here you can see what you have here are numbers representing the upgrades that we studied. And an upgrade is just a tuple, first version, second version. And here you have major upgrades, initial development upgrades, which are these releases that are labeled with the 0 version at the beginning. They are also allowed to introduce breaking changes wherever they want and whenever they want. And then you have the non-major upgrades. These ones refer mostly to minor and patch releases. So from the non-major upgrades, we know that we are not allowed, according to semantic versioning, to introduce breaking changes. From these ones, we saw that 20% of them were actually introducing breaking changes without informing their clients via the version number. So we said, okay, this is not good, but when we see like the general picture, we actually noticed that more than 80% of the upgrades are actually compliant with semantic versioning. So semantic versioning is not strictly followed, but it is widely applied in the wild. The second question was related more to how these principles have been applied over time. And what we notice is that in general, breaking changes are less and less introduced. But please notice on like the red line here, we see this one represents the non-major upgrades introducing breaking changes. This one is really like dramatically going down. And this shows us that in practice, as developers, we are trying our best to adhere to these principles. The final question we have is, what is the impact of breaking changes on clients? And personally, this was the most interesting one for me. So what we did is that we selected like the whole population of clients, depending on any type of upgrade. We sampled that population, and then we checked the broken clients, the ones that were actually being impacted by those breaking changes that were being introduced. And surprisingly for us, we saw that less than 8% of these clients are actually being directly impacted by the breaking changes. What's the main message here? That sometimes we are afraid of upgrading to the next library, or even as library developers, we are afraid of removing, for instance, certain features that are obsolete already. But if we see the numbers, this is not that bad. Maybe what we need is more information and tools that can actually tell us what is the impact of our changes. So thanks a lot for your attention. Here you can find the journal article and the pointer to Sonodo where we have all the artifacts we used. Thanks.
Thank you very much.
Thanks for the presentation. Great work. Can you explain how did you identify the users of the libraries, the clients that you mentioned?
Yeah, sure. Thanks. So we use a data set that's called Maven dependency graph. This one is based on a snapshot of Maven 2018. And this one already was modeled as a graph. So you can actually get all the dependencies among releases and clients. That's how we identify them.
Mm-hmm. Thank you.
Okay.
So 2 clarifications. When you say the clients were or were not affected by that, are you reading that effect out of the semver tagged edges in that graph, or are you building the code?
So basically what we did is we use this tool that I mentioned. Yeah. So we statically analyzed this, and based on that we reported the number of clients. Now obviously we needed to check the accuracy of the tool, right? Or maybe that wasn't your question?
Yeah, I mean that's kind of where I'm going. Semver is a human estimate of compatibility in the absolute, and has it's wildly over-compressed. It's obviously a lossy compression and kind of made up.
Yeah.
So the question is this evidence that semver quote unquote breaking changes are over-constraining, which would be nice to have a nice citation for publication.
Yeah. So
that's part of it.
Yeah. So actually, your point is. I find it fascinating because that's actually what we discover with this study. Sometimes we have this constant fear about semantic versioning in general, breaking changes in general, and then it's just, okay, we just need something like a simple tool that can identify this and give us the confidence.
Yeah, I would love to talk more. Also, there, yeah.
Ari,
Yeah.
we have to move on to the next presentation. I'm sorry. You can also find Ari during the break.
Yeah.
Okay? All right. Thank you very much.
Yeah, thank you. In this talk, I want to present to you how we can safely update automated dependencies in Java projects. My name is Andreas, and this is joint work with Ben, Hermann, and Eric Bodden. And it's quite a known fact that the use of open source packages is quite established, both in commercial and open source software. And the recent Log4Shell vulnerability has shown once more that vulnerabilities in the included open source packages pose a serious threat to the application. So developers must update known vulnerable dependencies in their software quickly. However, recent research shows that developers are actually hesitant of updating even known vulnerable dependencies because they are afraid of breaking the application. And this fear is not unjustified. And why? I have as an example here a very simplified dependency graph of a typical project on the right-hand side. On the left side is a project, and here in different colors are different open source packages. And here on the right-hand side, the green packages belong to one framework. And why is it complex? Because a Maven project easily contains more than 70 different dependencies. And the most of the dependencies are transitive. So developers only declare a few dependencies explicitly. The majority is automatically and transparently for the developers dragged into their application by the build automation system Maven without them actively knowing. And often vulnerabilities occur in transitive dependencies, so somewhere deep down in the dependency tree, here illustrated by the big red bug. And what makes it especially complex is that the naive approach of just updating that single vulnerable open source package often fails in practice, as a recent study by Hede shows. And why does it fail? And what is a naive update? So what do? We actually remove the vulnerable package from the dependency tree and also its successors, and simply update this single package to a non-vulnerable version. And during that process, new versions of the successors packages, so on which the vulnerable artifact and depended on, are automatically dragged in. And this can easily lead to conflicts. For instance, here, our pink dependency actually depended on version 5.8 of the blue package, but during the updating process, we actually included 5.11 of the blue dependencies, and this is then a dependency conflict. And we don't know if the pink one works flawlessly with the new version. So there are multiple requirements a safe backward compatible update has to fulfill. First, the blue dependency or the updated blue dependency and the previous one needs to be binary compatible. So the API needs to be binary compatible so that the pink package actually links and runs successfully with the new blue one. And if a project invokes the API of the package directly, the new update also needs to be source code compatible for the project to continue to compile successfully. And we have here dependencies belonging to the framework, and often these framework dependencies needs to be updated consistently. For some frameworks, they need to have the same version to work flawlessly together. And in all cases, the updated package needs to be semantic compatible. so that the runtime semantics of the API that this package provides does not change and does not break the runtime semantics of the application. And often, to achieve such safe backwards compatible updates, other dependencies often need to be updated as well, not only the single one. For instance, in our case, the green dependencies need to be updated and also the pink one to work with the update. And this is where our approach comes into place. We actually compute a set of update steps for multiple dependencies to achieve a compatible update or to introduce at least a minimal number of potential incompatibilities. And how do we do that? We construct a so-called unified dependency graph. That means we build the complete dependency graph for a project and also the call graph. And then we merge both graphs into the unified dependency graph. So each edge represents a dependency relation and also the APIs that a library or a dependency invokes on another open source package. And to respect framework dependencies, we actually collapse the different dependencies belonging to a single framework into one single node, so we can update them consistently. And to identify compatible updates or updates with minimal incompatibilities, we actually compute a min-st cut on the unified dependency graph. So we try to find a separation into two partitions, one containing the project and another one containing the library to update, with cutting only minimal edges. So because each edge represents API invocation from that library to another. And in the given example, this would be, for instance, a min cut. And then our approach looks at the remaining graph and tries to find a replacement for this graph that is compatible with updating the green and gray package. And how do we do that? We actually query a complete dependency graph of the main central repository, and we ask basically the following queries. Exists an update or newer version of the green packages to a non-vulnerable version? And we also query, exists a new version of the gray open source package with a dependency that depends on the version of the blue open source package that is greater or equal than 5.8, because the blue one is actually shared by the green packages and the gray package. And to identify a compatible update, we actually intersect both queries. So we ask, exists an update of the green packages and the gray package that both depend on the same version of the blue open source package. And as an output, our tool produces then update steps of multiple dependencies that developers can include as direct dependencies into their project. For instance, that the green packages needs to be updated and that the gray package needs to be updated to the version 7.8. To evaluate the effectiveness of our approach, we actually evaluated on a given data set of 380 projects from a paper by Heiderow, who evaluated the effectiveness of tools like Dependabot. And we took more than 3,800 naive updates that failed and checked if our approach can produce better updates with fewer incompatibilities. And our results show that in 1,500 cases, we found with our approach updates with fewer incompatibilities than the naive approach. And in even 70% of these cases, we found updates with no incompatibilities. Only in 14 cases we couldn't be found worse updates. Our approach computed worse updates. So to conclude, our approach can effectively produce update steps of multiple dependencies that produce fewer incompatibility than just simply updating the vulnerable dependencies like state-of-the-art tools like Dependabot propose. And we can even provide updates with no incompatibilities. For the future, what is currently missing is a user study that checks how understandable and the proposed update steps are, and if developers accept them into their project. Thanks for your listening.
Thanks a lot.
Thank you for your talk, a very brilliant idea. I'm from Nanyang Technological University from Singapore. I have two simple questions. Can you go back to your the diagram?
Yes, of course. This one?
Yeah. The first question is that why does the minimum cut has anything to do with the incompatibility?
So in our unified dependency graph, each edge represents a dependency relation, and also the APIs that a package or the project invokes on a dependency. And we try to find an update of the least amount of packages. So each edge represents a binary or source code compatibility. And we try to find an update that cuts the least amount of potential edges. So does it answer your question?
Yeah, understood. Okay, is this correct? Like, you can minimize the number of incompatibilities after the updates, right? But does that mean the incompatibilities would still exist in the dependent graph after the updates? Could probably still.
For some updates, we have incompatibilities. So we had the problem that even after an update, there were binary compatibilities existing. But as I said, in 70% of the cases, we found updates that have no incompatibilities.
Oh, okay, I see. Sorry, there's a second question. How do you define the framework, like the big one you merge them together into one big package? The Blossom compatibility, how do you ensure that?
For instance, we can input a user-defined list. For instance, dependencies with from this vendor or with this group and artifact ID belong to one framework. And we defined it, for instance, we said that org.spring framework minus boot belong to one framework, and also org Apache, Tomcat, they belong to one framework. Thanks for the question.
Yeah. Very similar question to in the previous talk. When you're describing incompatibilities here, is that you said something about looking at the call sites. Are you building and testing the code, or are you trusting Semver?
So to identify in this evaluation, we had two different approaches. First, we built the code and checked if the compile failed, and we also run the tests to see if the runtime fails. But what we also did is we built the call graph, and then we have all APIs that a package invokes on another. And then we use the tool SIGTest from Oracle to check if the API calls that are invoked according to the call graph are subject to binary or source code incompatibilities.
Very good. Cool. Thank you.
All right. Well, thank you very much. Thank you for being with Great and patient audience, I appreciate it. If you want to fill out the survey, you can scan this QR code. I hope you enjoy your lunch. Thank you so much, Andreas, for bearing with the technical issues, and thank you for the technical team for making it work. Yay.
Yeah, thank you for making it work.